Okay.
Can you see my screen, Paulo?
Yeah, it's nice. Okay, the next speaker is Gabriel Araújo from University of São Paulo at São Carlos, and he will tell about invariant involutive structures on Lie groups.
Thanks, Paulo. It's a pleasure to be here in the Colóquio. It's my first time in the Colóquio, actually my first time in Rio. The weather is lovely. And thanks for the organizers for the invitation to be here today. I'm going to talk about a class of involutive structures, which are systems of vector fields, which have many symmetries. So that's why we'll be talking also about Lie groups. First, involutive structures, they're actually a language, a good language to talk about systems of complex vector fields, which, according to the main theme of this section, we regard as first-order differential operators, partial differential operators. For technical reasons, in order for this theory to work properly, we have to look only at systems which convey the maximum quantity of information. Meaning, if you take commutators of equations you already have in your system, you don't get new equations. So what one way to express this is to impose that our system of vector fields is closed and under Lie brackets. Okay. As I said, this can be regarded as saying that our system of equations is somehow complete. And we encode all this information in a geometric object, which is a vector bundle. We will take sub-bundles of the complex tangent bundle of a smooth manifold. And such bundles will be called involutive whenever the Lie bracket of any two local sections of our bundle is again a section of our bundle. These sections of our vector bundle will be the vector fields in our system. Okay. Okay. And this kind of object, these involutive vector bundles, they occur very often in many fields, but especially in complex geometry, where most of the examples we usually study come from. And if you don't know much about it, you can just think of the Cauchy-Riemann operators in several complex variables. They are complex vector fields that, of course, commute. Okay. So about this object of involutive structures, we already have two classical textbooks, one of Travis and one to these three authors, and there are a lot of topics regarding the systems of vector fields are dealt with. But among them, which is the one thing that is of interest to me here, it's how to associate to an involutive systems of vector fields a differential complex, which plays a role vis-a-vis with the Ram complex in differential geometry, or they're both complex in complex analysis. Okay, and this differential complex can be regarded as a way to pose, and say algebraically, all the possible ways in which we can combine in a meaningful way all the vector fields that appear in our system in order to produce matrices of differential equations. Okay, just to give you two simple examples of this kind of feature, let's say I take n complex vector fields which commute. Well, a simple problem I can associate with them is this. Give a single function f, find me functions u1 to un such that this equation can be solved, okay? But I also can combine these vector fields in order to form other kinds of equations. For instance, this one. I give you now n functions, f1, fn, as my right-hand sides, and I want you to find a single function u solving all these equations, okay? This is the same u for all of the f's, okay? Now, however, compatibility conditions, they appear. A necessary condition is, of course, because these vector fields commute, is that the right-hand sides must satisfy all of these equations. If the fj's don't satisfy these equations, your search for a u to solve this system is just hopeless. And these conditions arise because the vector fields I started with, they commute, okay? So instead of presenting here the abstract definition of what would be the differential complex associated to an involutive structure, I will show concretely the equations that arise, provided we put a simplifying assumption on our system, is that it has lots of symmetries, okay? And our point of view will be global. It's inherently global because of the symmetries. We start with the Lie group, which is a smooth manifold in which you have operations that turns the manifold into a group, and the operations are smooth. And I would denote by L sub x the left translation by an element x. And we recall that a vector field on G is said to be left invariant, provided that whenever I push forward the vectors by every possible left translation, I reach the same direction assigned by the vector field x, but at a different point, okay? And not something else. Essentially, when I push forward x by any left translation, I get back to the vector field x itself, okay? And I will denote it by this German G, the space of real left invariant vector fields, and by C tensor G, the space of complex vector fields. And we know that these are Lie algebras, meaning that whenever I take the commutator of two elements in these spaces, they are again elements in these spaces. And we have the these isomorphisms, which we usually learn in introductory course in manifolds. Okay. Some examples: tori, they are Lie groups. They are compact and connected Lie groups, which are also abelian. Okay, the group operation is commutative. And left invariant vector fields on a torus are precisely vector fields with constant coefficients. Okay, and which were extensively studied by Greenfield and Wallach from the point of view of PDE. And we should keep this work of Greenfield and Wallach in our minds as we go on. Okay, so let's talk now about systems of vector fields. And just as a single vector field corresponds to an element in this space, I'm thinking about complex vector fields, okay? Then subbundles, which are left invariant, without being really very formal here, they correspond to linear subspaces of this complex Lie algebra, okay? And then involutivity, which is being closed under brackets, is translated into this linear subspace being actually a Lie subalgebra. Okay, so this is what I'm saying here is that to left invariant and involutive subbundles on a Lie group, they correspond in a one-to-one fashion to Lie subalgebras of the complex Lie algebra of G. Okay, so this is our main object of study. With this in mind, I can show you how the equations that we are interested in, they present themselves. So I take the Lie algebra associated with our system of vector fields. We take a linear basis of this as a finite dimensional vector space. They don't commute in general because I'm not assuming that my Lie group is an abelian. And I complete them to a full linear basis of our complex Lie algebra. Okay, this also don't have to commute in any sense. And so since the L's and the M's, they form a basis of this vector space, the dimension of our Lie group is M plus N, okay? And then we look at the dual basis of in G star, actually in the complex G star, which is dual to these vector fields, okay? These are actually left invariant one forms, okay? And given a Q, I will denote it by this space, infinity of G, comma, lambda Q, the space of all complex Q forms in G, which contain no zetas, okay? They can be expressed globally as combinations of exterior products of the taus alone, okay? With some smooth coefficients, okay? Here the notation is the traditional one for some multi-indices, order multi-indices. We denote by tau j this exterior product, okay? And I want to define an operator d prime which maps the lambda q to the lambda q plus 1, which is related to the exterior derivative on G. So what do? We pick an element here which has this form and apply the exterior derivative. So we go on applying the exterior derivative, and this part here, we copy here, and this part here we expand, and we got this. But now what happens is that zetas appear. So we must project everything back to the lambda q plus 1. And how do we do this? We simply delete every occurrence of any zeta k. Zeta k's they definitely appear here, but they might also appear here. But because all of these are left invariant one forms, we can prove that the differential of the tau j, they can be written as a combination of tau k's with constant coefficients. They must be complex because these are complex one forms, plus terms containing at least one zeta k, which we just ignore because we are trying to project this expression back to the set of forms that contains no zetas. So we just throw them out and we rearrange everything conveniently. And we reach this expression, okay? Where here we have constants multiplying the coefficients uj, and here some signs appear just so we can bundle the coefficients together to pair with the tau case. This is how we define our operator d prime, okay? And what we have here is actually a matrix of first-order differential operators. The entries of the matrix are these guys, okay, with real analytic coefficients, okay, because the zero-order terms are just constants, and the first-order terms are vector fields, which we assumed were left invariant, and because of that, they are automatically real analytic. And also, one can show that they form a differential complex, meaning that when I apply d prime twice, this is 0, okay? So this is the problem that we want to address. When I have f an element in lambda q, I want to find u an element 1 degree less, such that d prime of u equals f. And here, just as in the simplified example, compatibility conditions arise because since d prime square is 0, a necessary condition for the existence of solutions of this equation is that d prime f equals 0. Okay? I will give just a simple example here when such structures arise. So take M to be a Lie group with Lie algebra small m, and take as G the product of M with a circle. Its Lie algebra is just M O plus R. And take omega, a left invariant one form on M. And we denote by x the angle coordinates on the circle. And I'll take as zeta this one form minus omega plus dx. We regard both of this is in the circle. This is in M. We regard them as elements in the product, okay, as one forms in the product, so I can sum them. And this is the left invariant one form on G. And it defines an involutive structure V by declaring that X is a section of V if and only if X is a vector field that is annihilated by this one form. And this defines a left invariant involutive structure. with the underlying Lie algebra is precisely this set of, this star is just a typo, the set of complex left invariant vector fields, which are annihilated by this one form, okay? And concretely, if I take T1 to Tn a basis of M, and tau1 to tau1 the dual basis in M star, I can write omega as a combination of tau j's, because this is a basis of one forms, with constant coefficients, because I'm assuming omega to be a left invariant one form, in which case I can prove that a basis for our underlying Lie algebra is formed by vector fields of this form. Okay, this is very familiar for, it will sound very familiar for people who work with tube structures. Okay. Now we go back to the general case, and some questions that are of interest to us. One is to determine when the map D prime has closed range. We're dealing with the global phenomena here. Another thing is that since we are dealing with a differential complex, is to study the cohomology spaces of this differential complex. So we can ask a bunch of questions about these spaces. For instance, does it vanish? Which is just a way to deal with the question, is the equation d prime of u equals f always solvable, provided, of course, f satisfy the compatibility conditions? If not, is it finite dimensional? That's another interesting question. And as is usual in this business, we can also change these questions and to put other classes of coefficients, say real analytic, Gevrey, or distribution, or whatever it seems fit. Okay. Good. So let's recall a little bit some results due to Greenfield-Wallach for vector fields. This is the standard vector field on T2, where we're assuming the coefficient to be rational. And Greenfield and Wallach then characterize global hypolepticity in the two torus of such vector fields. It's in terms of an inequality of this type, which is the same as saying that alpha is not a Liouville number. And in the same volume, Greenfield also has a paper all by himself dealing with the analytic version of this. And he characterizes global analytic hypolepticity of these vector fields, which is in terms of a more elaborate inequality. And this is the same as saying that alpha is not an exponential Liouville number. But this inequality implies is implied by the previous one. So in particular, whenever L is globally hypoleptic in the smooth sense, L is globally analytic hypoleptic, okay? This is the first result that we are going to, we generalized for these involutive structures. So the next result we might regard the next result as a sort of Greenfield and Wallach on steroids, okay? Take a compact connected Lie group, not assuming to be the torus, but still compact. and take not only a single vector, not a single left invariant vector field, but a system, which for us is a left invariant involutive structure. The result we reached is that whatever the degree you look at, whenever D prime has a close range in the smooth setup, then it also has close range in the real analytic setup. Okay. If the cohomology space in the smooth setup is finite dimensional, then also is the cohomology space with real analytic coefficients. And in that case, they are isomorphic. They have the same dimension. And also, just because we can also replace real analytic in these statements by Chevrolet classes, or even more exotic ultra differentiable classes. Okay, the statements are just the same. Paulo, how much time do I have?
5 minutes.
5 minutes, okay.
Yeah.
Okay, so in these last 5 minutes, I will try to explain another kind of result concerning these left invariant involutive structure, and recall that the left invariant Q form is left invariant, provided it's pulled back by every possible left translation gets you back to the same Q form, okay? So, for example, regarding our forms that can be written involving no zetas with respect to, say, to some involutive structure, then this F is left invariant if and only if these coefficients are constant, okay? And these now quite old result, and I guess it's perhaps it's not even due to Chevrolet and Eilenberg, but it's contained in this paper, which has some original material, but it's actually a very readable survey of the state of the art of these of Lie groups and Lie algebras at the time. And it goes like this: if G is a compact and connected Lie group, then every closed form has a left invariant representative in the same cohomology class, meaning that for all closed Q form, I can find a left invariant Q form, which we should think of them as forms with constant coefficients in some sense, such that F minus G is exact. This is a statement about cohomology classes in the RAM complex, and it implies that among other things that all the RAM cohomology spaces are finite dimensional, but this is true for compact manifolds in general, but if you don't know that result, well, then you get it from this. And recently, Young, in his PhD thesis, he conjectured that some analogous results should hold for elliptic left invariant structures, okay, on compact Lie groups. And he attacked many particular cases of this conjecture, and I will show you a simple result in this direction. So back to our setup. G is a compact and connected Lie group. V is a left invariant involutive structure, and small v is the underlying Lie algebra. And using analysis, which is a elaborate form of Fourier analysis, and a pinch of algebraic theory of Lie algebraic cohomology, we could prove the following particular instance of the conjecture of Young, which is the following. Suppose that our involutive structure is elliptic, which algebraically we can read ellipticity like this. The sum of V with the complex conjugate of V is the whole Lie algebra. And we put an extra ingredient, which is an algebraic property on V that is semi-simple, okay, which is something related to the ideals contained in V. Then whatever F in lambda Q smooth, there exists a D prime closed, whenever F is D prime closed, I can find a G in lambda Q, which is left invariant and also D prime closed, such that F minus G is D prime exact, which is the precise generalization of this, but adapted to this more general involutive structure. Not for the lack of example, whenever we deal with, when M is a semi-simple Lie group, all these tube structures that we defined in the previous slides, they have this property of being semi-simple. And if you put some extra condition on the coefficients, you get that they are also elliptic. So for these structures, this theorem applies. I think I'm on time. And thank you very much. That's all I have to say about this.
Thank you, Gabriel. Questions, comments?
Gabriel, for this kind of result, you have something for Dubos complex, or that means try to study solvability in some sense?
Yeah, you see, you mean double complex and from complex geometry, right?
Yes.
Yeah, but well, in that case, the structure is elliptic.
Right.
So for instance, the first result that I mentioned about closeness of the range and finite dimensionality of the cohomology spaces, they all apply because the D prime has closed range on smooth coefficients, and actually the cohomology spaces are all finite dimensional. Regarding this second result, well, actually we don't have many examples of structures that satisfy this algebraic property. Okay. So
does not fit in this case.
Yeah, I never thought about it. I don't know if there are examples of probably are examples of complex structures that are semi-simple. I'm pretty sure there are, but I never. Max Janke dealt. He studied that kind of thing much more deeper than I did. Perhaps he's much more knowledgeable. about this. I think probably yes, but I'm not sure.
Okay. Very nice work.
More comments or questions? If not, let me thank Gabriel again